All right. Okay, so what we'll do today is we'll start with a kind of recap of Prolog or predicate calculus. So are there any questions regarding Prolog that you guys might have from the previous lecture from last Wednesday? Remember on Wednesday I showed you guys a program that uses the Star Wars universe, and we were trying to define what is a proper Jedi, what we consider as Sith tolerant, okay? We're using the negation operator, right? So are there any questions regarding that topic on last Wednesday? Any questions about Prolog? Like the syntax of Prolog, what is a rule in Prolog and that sort of question? No? Did anyone get a chance to download and install SWI Prolog so that you can actually play with the stuff that we talked about? Nobody. Okay. Well, guess what? Your next homework assignment is about Prolog, so you have to kind of download and install SWI Prolog. Okay, so let's start with that. Let's start with turning on the recorder, or double checking to make sure the recorder is on. Yep, it is. Okay, second thing is to go to the SWI Prolog website. So if you just type in SWI space Prolog in Google, the first link is the correct one. And you can kind of shortcut and go all the way to download SWI-Prolog and go pick the one for your operating system. Okay. So go to stable release, and then depending on which operating system you have, pick the correct one. And the Windows one has a Windows release note, so you might want to check that first. Okay. So we do have, the first link is probably what most people want. It says, SWI Prolog 8.0.2-1 for Microsoft Windows 64-bit. I think it will work on most, if not all, installations of Windows. The second one is also self-installing, but it's for 32-bit systems. I think it's kind of rare to find someone using a 32-bit version of Microsoft Windows these days. So that's kind of it. I know some of you use Mac or OS X. So the third one is for Mac OS X. So I think this covers most of the cases in this class. If you use Debian or Ubuntu, I believe SWI Prolog is one of the packages. So it's super easy to install it in that type of Linux systems. So do we have any additional questions about how to install SWI Prolog on a computer? Okay, no questions. All right, very good. Okay, so to use SWI Prolog, I have used it last Wednesday already. So if you just want to know how to load the file in, how to perform a query, that sort of thing, you can just kind of refer back to the video on last Wednesday. Because hey, if it's not operating system dependent, so it will work pretty much the same way, whether you use Windows or Mac OS X or Linux. So are we good so far with how to set up Prolog on your own computer? All right, very good. So what we'll do today is we'll look into the definition of cousins. Okay. And there are a lot of non-definition links to cousins. So we'll look up cousin definition. All right. So the cousin definition is pretty simple. A child of one's uncle or aunt. Okay. But what defines an uncle or an aunt then? Sibling of a parent. That would make this the first cousin. So what about second cousin? What is the definition of a second cousin? Share the same grandparent, but not the same parent. Right? So you have to basically skip and say, okay, this is the common ancestor, but there are no common ancestors below that particular common ancestor. that is kind of how cousins are defined. All right, so let's take a look at how second cousin is defined, and see what the internet has to offer, and then we'll draw a picture, and hopefully the picture will help us understand what a second cousin, third cousin, how those are defined. Okay, child of one's parent's first cousin. Oh, that's a recursive definition. I like this already. Okay, so what do you think the third cousin would look like? A child of one's parent's second cousin. That is good. That's recursive. So that means we can actually parameterize the first, second, and third, the level of cousins, right? Because it is definitely recursive. Are we doing okay so far with this? Now, it's difficult for me to explain this, but without using actual Prolog code, because that's going to be your homework assignment. Okay? So what we want to do is to ask a question. Okay, the predicate that we want to define. I can talk about that. Okay, so let's see. I have to shrink this back to the resolution of the screen. So this way I know how much you guys can actually see on the screen. So let me do this first. So I'm gonna go to Zerno. Okay, this allows me to kind of draw things in a free way. So there we go. Nope, wrong screen. One more time. There we go. All right. So what your homework assignment is going to be about is we want to find cousins, first cousin, second cousin, and so on. So what you eventually want to do is to define a predicate that is asking the question of whether two people are cousins or not. This may not be the best way to name it, so let me see if I can. Okay, maybe cousins would be a better way to name this particular predicate. So cousins is going to have three parameters. It would be basically asking whether X is Y's Z cousin. Okay? So X can be, let's say, Tom. Y can be Jack. Okay, lowercase, remember, because uppercase is uppercase is always a variable, and a lowercase is the name of an atom or the name of a predicate. So Z is going to be a number. Okay, so it can be like 2 in this case. So in this case, if Tom is Jack's second cousin, then this predicate will return true, and it will return false if Tom is not a second cousin of Jack. So are we doing okay so far with how the predicate is defined? So we are parameterizing the number of levels of cousin in this case. So you're not making one predicate for first cousin, another predicate for second cousin, and so on. We are making one single predicate for all the cousins. Is that okay? All right, so let's get back to the definition that we saw earlier on the website. So we get back here, and if you look at a third cousin, it's kind of like, cousins, X, Y, and then we have a 3 as the third parameter. Is that okay? So according to this definition, it's basically asking whether one is a child of a parent's second cousin. So now we have to rely on a child of a parent. Okay, so we need a parent-child relationship. We also need to recursively and say, oh, okay, now we need to ask about second cousins. Is that okay? We good? Okay. So it's not gender specific. In other words, there's no need to define awareness of gender in this case. We just need to know whether a particular atom is directly a child of another atom in this entire universe. So what that means is you will also need to define a whole bunch of parent of relationship or predicate. So you have to define parent of as a predicate, X, Y, uppercase, Well, okay, I'm using uppercase because I'm not giving you the actual parenthood relationship, but you would need to specify a whole bunch of parent-child relationship like this, and then you have to use specific atoms in place of XY. So you would have to say, parent of in parentheses, Mary, comma, Tom. Okay, so that means Mary is a parent of Tom. Is that okay? So do we have any questions at this point? So I want you to give me a family tree of at least 4 levels. So so at the most, it would be have one. Let's see here. We have individuals down here, father or mother, grandparent, and great grandparent. So we have to express relationship all the way up to a great grandparent level. Is that okay? Okay. Right. Now, but there's one thing that we have to be be careful about is how do we make sure that we can say that what makes a cousin different from a sibling? They do not have the same parents, right? So you have to now remember to express that because otherwise it will mention that siblings are also classified as cousins. Hmm? Z would be 0, yes. You can also call siblings the 0th level of cousins. If it's kind of weird, but as a computer science person, that seems to be logical. So are we good so far? So let's take a look at a picture, right? So we'll take a look at a picture of people, individuals. So A is one of the great grandparents. Okay, so this is a very simplistic tree. I'm hoping that you guys will give me a more realistic tree, but I'm giving you a very simplistic tree here. So we have, I guess this type of a tree is good for aphids because aphids can do asexual reproduction. They don't need 2 genders to have offsprings. So this tree would actually be suitable for aphids because they can have one single parent and not 2 parents. Okay, nobody's getting it. You're getting it? Okay. And not too many animals can actually do that. Snails would be the other ones, but snails are interesting in the fact that it can do both asexual and also bisexual reproduction, depending on the environment. If the environment is good, they use asexual reproduction, which basically means I think I'm good enough, there's no need for improvement. So they would do asexual reproduction when times are good. And then when times are bad, like there's predator pressure or food issues and whatnot, then they'll do bisexual reproduction. Hopefully, to get just have mutations or combination of factors to improve their gene pool or to have basically in order for evolution to work. So, kind of interesting, but not related to programming. B, C, D, and then we have E, F. G, H, I, J, K, L, M, N, O, P, Q, and R. There we go. So now we have a 4-level parenthood tree. So we can now say that A is a parent of B, B is a parent of E, E is a parent of K, and so on. Okay? So the question is, what is a sibling? A sibling would be 2 individuals sharing a single parent, right? So you can say that K and L are siblings because they share a common parent of E. So then we look up what is a cousin. Okay, so we get back to just a single level cousin first. And according to the dictionary's definition, a child of one's uncle. And then it also says, a person belonging to the same extended family, a thing related or analogous to another. Okay, So, but it doesn't really give you a definition of a child of one's uncle or aunt. So it's basically a child of, um, but not the immediate parent. That is the key. Is they do not share the immediate parent.
So they share a grandparent, but not the immediate parent.
Correct. So that is the first level of cousin that you actually have to define, because without that you cannot really define the second, the third, and the other levels of cousins. This is the base case, so to speak. Okay, you cannot get any lower level than just the first level cousin. Is that okay? So when you look up the second level cousin, or second cousin of somebody, then the definition of the second cousin is the child of one's parents' first cousin. So if I am the person, if I am the one, okay, so my parents' first cousin's child would make that person a second cousin. Is that okay? So let's look up the tree here. Okay, so we'll try to do it this way, and we'll try to move this to the side. Nope, we lost the tree then. Okay, I'll draw something first. You may not see the tree. So we have to define what is a. So let's say, okay, so let's say K is me. Okay, this is TAC, and I'm looking for a second cousin. So where's my second cousin? According to the definition, I have to first look at my parent, which is E, and then E's first cousin, or one of the E's first cousin, is what? Okay, I'll put this picture back here. G, H, I, J, those are all first cousins of E. But F is not, because E and F are siblings. So now, if you look at G, well, I don't really have a second cousin from G, because G has no offspring. But I do have H having two offsprings. N would be a second cousin of me being K. O is a second cousin of me. P is a second cousin of me, mine. And then Q and R are also second cousins of mine. Is that okay? So in this picture, we can only go as far as, let's see, we can only go as far as third cousins. No, second cousins would be the only one. Because when we go all the way back to A, then it doesn't work. Is that okay? Let's see. Let's double check. Cousin. To get to what? Third cousin? So this can handle third cousins. Need more ancestors. Yep. Okay. So second cousin is the best you can do. So if you want to make this even bigger, have this being a subtree of another ancestry tree, they can also track down third cousins. But with only 4 levels of generations, you can only specify up to second cousins. So are we good so far? Now this only specifies one grandparent, or one parent, one of 2 parents, of assuming these are all humans, or at least individuals that require 2 parents. So if you have a more realistic tree, then it gets a lot more complicated, because you got 2 parents to each individual. So now K has 2 parents, and L, even though it's a sibling, okay, doesn't have to share the same 2 parents. They only have to share 1 parent to be siblings, right? So now you have you have some kind of interesting rules if you want to kind of track down when you have more than 1 parent, because it's not a tree anymore. It is no longer a tree. Yep.
So the lowest level is individual, but everything above.
They're all individuals.
But E you said is parent, so it's 2 individuals.
E is an individual who so happened to be a parent of K.
Oh, just one. Okay.
Yeah. So if you want to also account for the other parent, then you can have e prime being the other parent. So now you have this kind of relationship, because e prime as the other parent is also a parent of k and a parent of L, assuming that they share this both parents, right? Which does not have to be the case. Yep.
Would it be somewhat easier to just associate one parent to two children, just because of the scenario that one of the two children doesn't have to have the same second parent? Do you know what I mean?
So you need at least one parent, right? So the parent. Um, okay. So when you go back to the definition of a second cousin, it says a child of one's parent's first cousin. So that means it can be either of the parent. So it depends on the culture, because in certain cultures, like the Chinese culture, they have a specific name for every different type of cousin. So it's not just, first, second, and third cousin. It's also, is it the second cousin from mom's side or dad's side? And then also, as you traverse the tree, are you following the mom's side, then dad's side, and then mom's side? They all kind of have, special words for that, which I don't know. They're too complicated. I just use the word cousin. But you can see how this can get much more complicated when we introduce, gender into individuals, and then we track down genders in that case. So that makes it very complicated. So I don't need you to make it so that complicated. We just want to be able to locate, cousins, first cousin, second cousin, and just ancestry in general. So are we good so far? Yep.
So in our assignment, do you want us to have like just one direct descendant, or do you want like somebody inheriting or transferring the tree?
Could you ask that question again?
For our homework tree,
Yep.
do you want just the direct descendants, like, or do you want?
You will need direct descendants first. You would need a parent of as the base rules. So you have a whole bunch of those in order to specify that tree. Okay, let's get back to the tree, and I'll tell you what it looks like. So if you look at this tree, you have a whole bunch of what we call ground rules, which basically are rules that only involve atoms. There are no variables. So you will have your parent of AB, parent of AC, parent of AD, parent of BE, parent of BF, and so on.
Yeah,
Yep.
basically, do you want us to have E prime or no?
That's up to you. That is up to you. So if you want to put in like a recent actual tree of ancestry of your family, you can put in all of these as far back as you can trace. Then you can find out who classifies as your first cousin, who classifies as your second cousin, and so on, which can be fun. It can be very interesting. Yep.
Can this like avoid that problem by just using like pairs for parents? Like parent A, parent B would be one node, and then list their descendants. What if you have half siblings?
Then you cannot account for half siblings, right?
Okay.
Unless you have parent BC as well as AB.
Like represent children too.
I think it's better to, if you want to keep track of all that stuff, it's good to, okay, this is getting back to database concepts. You want your database to be normalized. In other words, each individual item, each data point is as independent from other data points as possible. So you would express parenthood as one thing, and then you will also express gender as a separate thing. So you would basically say, um, is parent of Mary Tom. Then you would have is female Mary, okay, and then you will have is male, Tom. Okay. Now I'm not saying anything about non-binary gender, but I'm just saying that assuming binary gender is what we want to be able to account for here, then that's what we need to do. Is that okay so far? Okay. So that will be kind of interesting because you can also now specify, give me all the people where Mary is a grandmother of. right? Because you can write that, once you know gender and you know how many generations you need to look into, then you can also define those, ancestry relationship. Is that okay? Yep.
So is this tree starting with two nodes, like two, one, one parent and then another parent,
No, this
or
tree is
for
only
our assignment?
for your assignment. It is up to you. You can have something as simple as a tree like this, okay, which is not a whole lot of fun. I mean, you can define all the individuals from A to R just like this. You can just copy this into your code, but it wouldn't be a whole lot of fun, right? I mean, but if you enter your actual ancestry, tree, that's kind of interesting. I mean, okay. The good thing about entering your own family tree into the homework assignment is you can verify your answers. You can say, right, cousins, Josh, comma, uppercase X, comma 2. That should return all the second cousins of you. Now, if it returns, something other than a second cousin, like an uncle, a grandparent, a sibling, or something like that, that means your code is not correct. If you use this particular tree, you can still kind of do that, but it's harder because it's not intuitive that you can look at this tree and go like, oh, I know these are second cousins of mine. So entering actual people can be helpful in that case. Is that okay? Yep. Question? Nope. Okay.
And make people up.
Huh?
And make people up to fill in the gap.
Absolutely. You can put all the famous people into your family tree. It can be completely made up. You can even copy characters from popular culture. So family trees of, I don't know, Game of Thrones or whatever, that has enough generations, that would be helpful. Okay. Huh? You can steal from somebody else's history. Yep. And I have a, well, I don't know for sure. I think, but some people may end up doing a genealogy research, because of the homework, which is kind of cool. Because you track your way back and they go like, oh, I can only track all the way back to my great grandfather just based on my own memory, right? Then you start to ask, people that your relatives, and go like, so, who's the father of my great grandfather? And then you might have to ask a few people before you get an answer. And then imagine you have one more node on top of this, but that brings you another whole tree. And that entire tree are your third cousins. Right. Well, not the entire tree, but the bottom level of the entire tree at the same level as you, those are your third cousins. Those are relatives that you may not even know about, which is kind of what genealogy is about, right? I mean, you get to find relatives that you did not know about at the time. So are we good so far with this homework assignment? Just kind of the general idea. I will write it up, make sure that we understand all the full specifications. But to get started with this one, you definitely need to have the parent of relationship first. Okay, so you have to define a whole bunch of parent of relationship. Just based on this tree, and you also know that the key or what I'm really looking for are the cousins. So so you can start to kind of thinking about how do I specify a cousin and not accidentally identify siblings as a cousin, because that's the key issue is how do I make sure that I do not look at K and L and say that they are cousins. So are we good so far with this homework assignment? All right, so you can kind of play with this for a little bit, and then I'll go write up the actual description of the homework assignment, create an area where you guys can upload your Prolog files, and then I give you like names of the predicates. So right now these two are now official. Okay, so your cousins predicate has to be like cousins with 3 parameters. The first 2 being the individuals, and then the third one being the level of cousins. And then you also need parent of as a predicate as well. Yep.
For the third parameter to the cousins thing,
Mm-hmm.
are we gonna have to actually specify numbers somewhere? Because like, what if you just have like a number somewhere? How do you know it's not gonna put a column as like the third argument or like some random person's name?
So okay, so that's a very good question. So numbers like 1, 2, and 3, those are also atoms, which means you can have a ground rule that has one number like 1 specified in place of z. So that would be the basis of your recursion, because when things hit all the way down to 1, then it will try to match the predicates or the predicate or predicates that ends with 1 as the third parameter. Yep.
You just have like a rule somewhere that's like cousins x y one.
Yes. Yep.
So if you did like cousins x y z after that rule, would it try and just do every number? Like all infinitely go through all the numbers and try and find any case?
Yep. Yep. That's right. Okay, so that brings up the necessity to talk about numbers in Prolog. We're not going to do a project with this, but it's good to see it as an example. Okay, so the example that we want to look at is factorial in Prolog. All right, so this kind of gives you an idea of factorial. In this case, the second parameter is the actual factorial. It is the factorial of the first one. Now remember, Prolog is not a general purpose programming language. It cannot really return a value. Okay, it's not like in C and C++, you can say, oh, if n is 0, then go ahead and return 1. So what the first predicate is talking about is, yes, the factorial of 0 is 1. That's all it's saying. It's just relating 0 and 1 and say that 1 is the factorial of 0. That's all it is saying. Is that okay? So now we look at the second, the second rule. And by the way, yes, you can break up the conjunction into multiple lines. Prolog is not sensitive to indentation nor line feed. So you can break it up into as many lines as you want. Okay? So what this is saying is f is a factorial of n only if the following are all true, because they're all separated by commas, right? Because if you use a comma as a separator for the right-hand side of a rule, a comma basically says conjunction, and. So what it is saying is f is a factorial of n only if n is greater than 0, and n1 is n minus 1, and f1 is a factorial of n1, and f itself is n times f1. That is how you specify factorial in Prolog. Yep.
So like if you wanted to do looping in general, you would just do it recursively like that.
Hmm?
If you wanted to do like a loop in general, you just do it recursively.
Yes.
What about like ifs and elses and stuff?
What about
Like if elses?
if else's? Those would also be predicates, because you can have ors.
Oh, okay.
Yep. So once you have ors, then if the first rule doesn't fire, then the second rule can fire. That kind of takes the place of a if then else, which is a weird way to do it, but that's how it's done in Prolog. So are we doing okay so far with these two clauses? Each rule, by the way, is also called a clause. But are we doing okay so far with this? Can someone tell me, in the second rule, okay, not the first one, in the second rule, do we have a particular variable that is existentially quantified? This kind of relates back to something that we talked about in the previous class, something that has to do with whether a variable appears on the left-hand side or the right-hand side of the colon dash symbol. So do you guys still remember which one is which one? If a variable appears on the left-hand side, it is blah, blah, blah quantified. What is that blah, blah, blah? Universal, that's right. So n and f are universally quantified. That means things that only appear on the right-hand side being existentially quantified. So that would be our n1 and also our f1. Okay? So that means the actual way, the long way of reading the second clause is a little bit confusing, but this is what it's saying. It says for all n and for all f, because those two variables are on the left-hand side. They're universally quantified. So we say for all n and for all f, if n is greater than 0, and there exists n1 being equal to n minus 1, and f1 is the factorial of m, there exists f1 that is a factorial of m1, and f equals to n times f1, then f is the factorial of n. That is basically what it's saying. Okay, you guys are looking at me go like, okay, could you say that again? The answer is no. I'm not going to say that again, but instead I'm going to write it out, which I think is a slightly better way. And where's my notepad? It opens it somewhere, but it doesn't put it into this window. Yeah. Okay, we'll do it one more time. Oh, okay, maybe I just didn't click it correctly the first time. All right, so we'll write out the statement corresponding to the second clause of factorial. Okay, it's saying for all n, for all f, okay, there exists, okay, so it depends on how you want to embed, because you can certainly embed things, in this particular way. You can say, let me see here. Okay, there we go. We need this thing, f equals to n factorial. So I'm putting the left-hand side of the rule to the left-hand side of the rule to the right-hand side of the implication, which is what it is supposed to, where it's supposed to go. So what goes into this pair of parentheses would be the right-hand side of the rule as a conjunction. Okay, it's kind of big as a conjunction. So what it is the first thing is pretty simple. Okay, we have n being greater than 0. Because at this point, n is already bound to something, because we have for all n all the way on the outside. So n already is a particular thing, and we can now say, is that thing greater than 0? Okay, if it is greater than 0, what if it's not greater than 0? Well, if it's not greater than 0, then the implication is automatically true. Yep, okay. So now we have to say, and. So after the and, we need the existential thing. So now we have to say there exists n1 such that n1 equals to n minus 1. And then we have to specify a whole bunch of other things along with this too. But is that okay? I mean, if I give you an n and we know that n is greater than 0, would it be a problem to find an n1 such that n1 is n minus 1? No, it just uses a lot of words to describe n minus 1. But we need n minus 1 to be in a particular variable, because we need to use it over here in the second clause. Yep.
Let me make sure I understand like how you're doing it. So you would give it like factorial of like some constant,
Mm-hmm.
and the second argument would be general. It'll search through values for the second argument until it hits a true, where it's going to spit out like factorial of blah is true, and that blah is going to tell you that something equals something factorial.
So we'll get to how it works a little bit later, but we'll finish expressing this whole thing first, and then we'll get to the mechanism of how it works.
What I'm asking though is like it's not returning a number; it's going to return a predicate.
Yes.
That implicitly has the answer that it's equal to.
Yes. So the way you ask the question is, you can say factorial 1 comma 3. It would just return false. It's like, nope. But you can also ask a question like, factorial 6 comma uppercase x. Then we'll find that uppercase x is, let's see, 5 factorial is 120. So 6 would be 720. So it would basically find the answer, in that particular process. But we'll finish this first, and then we'll get back to that question. Okay, so we need n to be n1 to be n minus 1. And now we have the second predicate, which basically says, and there exists f1 such that f1 is n1's factorial. And then I'm not sure how many levels of parentheses I'm in already. And then you have another and here that says f equals to n times f1. That is basically, okay, not counting the nesting of the parentheses. This is basically what that rule is specifying. Is that okay so far? Good. But how does it work? Okay, that's basically your question, is what is the mechanism of Prolog when it encounters something like this? So we'll go ahead and find out what is, okay, I'm not going to spell the entire factorial. So let's say we use exactly the same example that we used earlier. Okay, we ask Prolog, okay, with these clauses specified, we ask Prolog, what is factorial 6 and then uppercase x, which is basically saying, give me all the values who are factorials of 6. Now we know there's only one value that fits that description, but Prolog does not, right? It will look at this and go like, okay, who's a Jedi? Okay, find all the Jedis. Who's a proper Jedi? Go find all the proper Jedis. It will try to find all the things that fit this particular description. So what Prolog would do next, okay, I need to scroll down a little bit because I need to display the other rule or the other clause as well, is it will try to match these predicates in the order that they are specified. So the first thing it will do is, okay, can we quote unquote unify this? Okay, let me just write the entire thing. Can we unify fact 6x with factorial 0, 1? In other words, can we use some kind of substitution to make these two the same? The answer is no, you cannot. Because substitution requires a variable. You cannot substitute atoms with an atom with another atom. You can only substitute a variable with an atom. You can also substitute a variable with another variable. That is okay. But in this case, they cannot unify. We cannot make those two match. Okay, so the answer is no. Now we try the second rule. So we say, can we unify factorial 6 variable with, okay, typo here, fact nf? The answer is yes, okay? It doesn't say that 6 is a factorial of x. It says, yes, we can fire this rule and check it out. That's all it's saying, okay? Unification means, these two, the description of 6 can be used to substitute a variable n. X as a variable can also be used to substitute another variable f in this case. So now we go into the rules knowing that n is 6. We have that substitution of n being 6. So now we have to check out whether 6 is greater than 0. Yes. Now we have to invent an n1 so that n1 is n minus 1. Now when you use the word is, it is kind of like comparison, but it also goes a little bit beyond comparison. It basically can solve for the left-hand side. So you can ask the question of, is 6 is 5? Okay, you can ask the question. Then it'll come back and say, true, it's cool, okay? But you can also ask, question mark, n1 is n minus 1. Then it will actually do the computation and compute n1. So it doesn't do the dumb thing of looking at all possible integers and find the one that is actually n minus 1. It knows how to do calculation and say that, oh, n1 is 5 in this case. Okay? So that means n1 equals 5. So now we have, yeah, go ahead.
I just have a quick question. The is
Mm-hmm.
the syntax that you would use when you were writing the Prolog?
That is correct. Yep. We can put this into a SWI Prolog later on and actually see how it works. Okay, so at this point we have n being bound to 6, n1 being bound to 5. So when we use the word binding or bound, we're basically saying, do we know what this variable is associated with as an atom? So n is already bound, n1 is also bound at this point, and then we get to the factorial. So now we ask, okay, what about the factorial of 5 and then with a variable f1? So with that, what Prolog is going to do is it will go treat this subproblem first. It will do quote-unquote recursion. In other words, it will try to find the factorial of 5 first, or confirm or disconfirm that 5 has a factorial of some kind. Is that okay? So we do the recursion, but just like the way we need to look at recursion in any class, we basically just be lazy and say, let's say it works. Okay, so let's say it works. Then by the time this is confirmed, then f1 is going to be bound to the actual factorial of 5. So now it will say f1 is now bound to the value of 120, which is the factorial of 5. Then we'll have the last one, which is f is n, but we know what n is. N is 6. We also know at this point what f1 is. F1 would be bound to 120. So these two will now give us, basically f is now bound to 720. And because each one is true, 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 and true, then the whole clause will only come back and say true, but it will also say, in addition of being true, that x is 120. Are we good so far? Kind of? Okay, so yeah, go ahead. Absolutely. So we'll type this program in and actually see it in action. So new window. And I'm not going to copy and paste, just because sometimes when we copy and paste, certain characters that we see as some character does not turn out to be that character. Only if n is greater than 0 and n1 is n minus 1 and f1 is n1's factorial and f is n times f1. Okay. Save the file as factorial.pl for Prolog. And by the way, the extension is important. So when you save a file in SWI for SWI Prolog, you have to make sure the file extension is PL. Okay, so that part is kind of important. It is not the operating system that is doing this. It is SWI Prolog itself that's enforcing that extension. So we say SWI Prolog, and then use square brackets to bring in or read the file that you wanted to read. In this case, it's factorial. When you specify the file name, do not include the extension. And this is why the extension is important. Because if you, I need to move this up a little bit. So this is why it is important to save it under the right extension, because when you specify which file to load, you only specify the file name part, but not the extension part. The extension part is implicit. Okay, again, don't ask me why this is the standard, but it is the standard. So you press the enter key. If you say false or an error message, you might have specified a wrong path, or you're not in the path that you thought you were on, and so on. But now it is there. So now we can ask, okay, let's try something stupid first. Okay, it says true, and then false. It basically says that there's no other way to make it true. And then we can ask something that is definitely not true. It says it's false. Is that okay? So now we can ask something other than 0 or, this is already not 0, not 1. So in order to determine that the factorial of 1 is not 3, it has already used the recursion. Because this would have failed fact 0, 1, which is our first clause. Then it will go to the second clause and actually try to use recursion. Is that okay? So now we can ask it, what is the factorial of 6? And it says it's 720, and it says there's no other way to find, there are no other factorials of x. Are we doing okay so far? Now remember the what does the semicolon mean again in Prolog? A disjunction, or, right? So it still makes sense, because when we ask, is 1 the factorial of 0, the actual full answer is true or false. But true or false is just true. Yep.
So is this like an indentation because we're in Prolog? Is it going to perform as well as if we wrote a recursive factorial in C, but worse if it fails? Because if it succeeds, it's essentially the same thing as if we wrote it in C, but if it fails, it has to check other cases.
It will backtrack automatically and check the other ones. Yes.
So if it fails, then it'll perform worse, but if we give it something true, it'll perform just as well.
Not entirely true. So even if it's true the first time, you go all the way to the end of the entire conjunction and everything is true, it will give you that answer, right? Then it will go back and see if there are additional answers. It always backtracks. Yep. If you want to stop Prolog from backtracking and you just say, I just need one answer, there's no need to find other answers because there are no other answers, then you have to use what we call a cut operator to basically do not backtrack beyond this point. But this is kind of how it works. The other way does not work. You cannot solve for the fact whose number's factorial is 120. That does not work. It has to do with the operator is only goes in one direction. It can only use the right-hand side to determine what is on the left-hand side. Yep.
Create a third clause to solve for that?
I'm thinking about it. You will have to ask, so you have to do a division, right? And confirm it the other way. Because what you're doing is you're reversing the two sides of the is, and then confirm it in a different way. So let me get back to that question, and let me answer his question. Yep.
Say again, why get backtrack to say to check if there's another answer?
That's a good question. Okay, so remember your question so I can backtrack to your question later. See, I can use the word backtrack too. We can backtrack to the backtrack question. Okay, no one is getting that one. All right. Okay, so the backtracking is really helpful when you ask, give me all the second cousins of k. Remember that question earlier? So let me use a different color this time so I can highlight what Prolog is going to do. So depending on how you write your code, okay, but most programs to find cousins of different levels, it's going to do something similar to what I'm going to highlight. So it would go ask, okay, give me. So we need to find the child of a first cousin of mine, okay? No. We have to find a. Right, the child of my parents' first cousin. Right. Okay. So it will be able to find. In this case, n will be the first answer it's going to be able to find, depending on how you define the parent-child relationship. So I'm assuming the way you define the parent-child relationship is following a depth-first search order. So that in that case it will find n first. So you got one answer, right? Assuming your original question is k, comma, uppercase Y, comma, 2. So it will come back and say that, yes, we have at least one person in this entire tree who is my second cousin. But if you do not use a cut operator, what it's going to do is to ask, oh, do we have other second cousins? So it's going to backtrack to this point here of locating my parents' first cousin and ask, does that person have another child? Is that person parent of another individual? And the answer is, oh yeah, is O. So now the Prolog engine will also give you an answer of, oh, by the way, O is also your second cousin. At that point, it will try to find another child of H, which it will find none, right? Then it would backtrack to here and ask, does D have another child? Because we're trying to find the first cousin of my parent, right? So it will try to find another child of D, and it will find that, oh, another child of D is I. Then it will go down the tree again. So basically, eventually, it will find that P, Q, and R are all second cousins of K. Now, at this point, after it identifies that R is a second cousin of K, then it will try to backtrack, right? It will go back to J and ask, does J have another child? False. Doesn't have another child. Then it will go back to D and ask, does D have another child? False. Then we'll go back to A and ask, does A have another child? False. And that's why you end up with false, false, false. And there's no way to make that the right-hand side of that clause true anymore. And as a result, it will give you a final false because it has backtracked, examined every single possibility, and this is all we can get. Yep.
For like backtracking and functions that take numeric values, how does it know like when to stop backtracking?
So you're talking about the factorial example. I think the is automatically stopping the backtracking. Because is it's no longer okay. So let me get back to here. So let's just say that we are talking about. Okay, switch back to the normal color. So when we ask, okay, so let's say that we know that I is bound to 6 already. Okay, then we say there exists a J such that J equals to I minus 1. So the way Prolog does this, even though conceptually it is still an existential relationship, which basically means there may be more than one J that fits this requirement. So technically speaking, when you look at it strictly from the existential perspective, the Prolog engine has to re-examine, basically all the other integers other than 5. There may be another one, right? But in reality, it does not, because when you use the word is, it is binding the right-hand side to the left-hand side, and it's also doing an implicit cut of saying, nope, there's no other way to, there are no alternative to this existential quantifier. So is that making any sense? So which also makes a lot of sense in reality. So if your is involves comparison, that becomes an interesting thing because when you say something is greater than something else, then you're opening up to more possibilities. Well, that brings up a very interesting question because we can now write a different program. Okay, so are we good with this program? Can we move on to another example? So we're good with this one? Okay. So let's go ahead and move on to a different one that looks really innocent, but I think this is a good test of how Prolog internally works. Okay, so we'll just say g of xy only if x is greater than y. Okay, a very simple predicate. It's all it says is greater than. Is that okay? So we'll save this. We'll call it g.pl. And then we switch back to here. I think you can just reload it by using a square bracket again. It will clear what you have already and then load the new program in. Okay. So now we can ask, okay, is 1 greater than 3? False. Okay, pretty easy. Is 3 greater than 1? True. Okay, that's good, right? What if I ask it, 3 is greater than what? Now, remember, these are the x and y are both universally quantified, right? So it says, for all x and for all y, if x is greater than y, then g of xy is true. Basically, that's what it's saying. And we know that Prolog can backtrack, which basically means once I find an answer, it has the mechanism of going back and say, do we have another answer? And let's see what happens. It cannot do it. Okay, but the error message tells you something. Arguments are not sufficiently instantiated. The underscore 2002, that is the internal variable name, for x. So this is the problem. Note, some frames are missing due to last call optimization. Rerun your program in debug mode. So it cannot deal with this. So comparisons, cannot backtrack. It can only work on actual values, but it cannot say, let me find you something that makes this true. That does not work. Is that okay? So certain operators require atoms to work with, like greater than in this case definitely requires an atom. Is also going to make sure that the left-hand side ends up as an atom, which means the right-hand side also needs to be atoms as well, cannot be just variables. Is that okay? Now, none of this, except for one, is going to affect your program, because in your program, the only part that is numerical that involves comparison would be the level of cousins. That's the only part where it comes in handy when you need to do comparison. And also using the is operator. Are there any other questions about this? Yep.
So like the closest thing you would have to an actual assignment, would that be what we were doing with Factorial with the internal variables, the stuff that was on the right hand side?
Yep. Yep. You would need to look at the Factorial example to understand how to introduce an existential variable on the right hand side, because that's what you need in order to express we are looking at a child of the first cousin of my parent. Is that okay? Are we good with this particular topic? Yeah, go ahead.
Does it actually not have arrays at all? Like if you wanted something like an array, would you kind of do something like
It has an array. Since you asked, I'm going to talk a little bit about it. It does have the concept of an array. We do not need arrays in this particular homework assignment. But if you look up arrays in Prolog, it does have the concept of a list. And then you can index items in the list. The other thing that's really cool is you can extract the head of a list just by saying square bracket, and then you use a variable x and then specify xy. Then x automatically becomes the head of the list, and then y becomes the tail of the list. So you can disassemble a list into the first versus the rest of the components really, really easily. So I'm not sure whether you guys really want to kind of dive into this, but you can see how Prolog has the concept of a list using square brackets, and you can process it. It also has has function as a part of its repertoire. It understands what a function is. A function is nothing more than a mapping from. It's a mapping where the domain is your universe, and then your codomain, your codomain is also the universe. So it just maps stuff around. But remember, this is not needed for your homework assignment, and we are not going to talk about lists in Prolog in this class. So are we good so far? All right. So before this class, does everybody understand, the definitions of your first, second, third cousins and so on? Most people did. Okay, very good. So that means the semantics of those words are not a barrier. It's really just a question of how do we code it in Prolog. So you will need that. You will also need something from the previous example that I did, because you need to use a backslash plus for negation to make sure that somebody, so that you do not classify siblings as cousins. So that's something you have to work on too. All right. Anything else? Anything related to Prolog programming? Yep.
So my question earlier,
Oh, right, backtracking.
if when you had a number and find what is the factorial of that number,
Right. Okay.
but you couldn't give the factorial and say what is this number factorial?
Okay. That's exactly where we were leaving off. So okay, let me go back to that. Oh, that's the one. Okay. So this particular, not that one. Where did I put it? There we go. Okay, so this helps us to find the factorial of n. If you want to confirm that n's factorial is, or whose factorial is f, okay, if you want to find whose factorial is f, then you will have to change these. The is the problem, because in this case what you need to do is to work with f first. So you basically want to say f1 is f divided by n, right? And then you pass that along here, and then you specify f divided by f1 is n. No, the other way around. Okay, so let's.
If you wanted to say f1 is f divided by n, it still doesn't know what n is. But when you get to
Okay, so to reverse it, you will still have a predicate like this, but n is not given, so you cannot start with n, right? So you have to start with, you will have to start with f. So f has to be greater than 0. And you also have to think about when you have to stop the recursion too. So when, so to stop the recursion, you will have the same thing, because that works in both directions. So in this case, f has to be greater than 1. And then you say f1 is f divided by, I'm not sure whether this is integer division in Prolog, but we'll assume it is, okay? So f1 is f divided by n, but you don't know what n is. Oh, okay. I see what the problem is. There's no way to specify that. So I don't know how to, because if you're given a number, you cannot get back to the one step before if you cannot even confirm that number itself is even a factorial itself. There's no easy way to do that.
I couldn't even think of how I would do that in C.
Well, if you want to do it in C, you can just test it, right? You can just use a while loop to go through all the possible n's, and then when you can see that 1 factorial is less than, but the factorial of just the n plus 1 is greater than, then you know that that number is not even a factorial of. Yep.
Is there a way we could do it in terms of the other factorial? Like in this factorial, you start at a point and you keep checking factorials.
Yeah.
The other factorial to
Yeah, you can.
figure down.
Yep, you can do that.
It'd be inefficient.
It'll be very inefficient because you're just testing it, right? Yep. Yes, it is.
What if the number you're testing has 800 digits?
That sounds like it'll be an horrible thing to happen.
Yep, it will take a while.
Ah.
Okay. All right. So getting back to your original question is there's no quick and easy way to do it. So reversing and find out whose factorial is a particular number is not easy. It's not an easy problem to solve. Okay, so let's get back to the browser.
I guess that's why calculators don't have an inverse factorial.
In theory, you can make, there's no inverse. Okay, so that's a very good question. So does factorial have an inverse function? It brings, doesn't that bring up good memories, like what classifies as a function, all the surjective stuff, injective stuff. So now the question is, if you look at factorial, first of all, is factorial a function? And I'll give you the domain and the codomain, right? The domain would be all the natural numbers starting with 0. The codomain would be all the integers greater than or equal to 1. So would that make factorial a function? Okay, I'll give you the representation here. Yes, the answer is yes, it is. So let me just kind of write it out here. So the question first is, if f is factorial, okay, and we are looking at natural numbers as my domain, and we are looking at the codomain being all the non-zero, all the positive integers excluding 0, okay? And the question is factorial even a function? The answer is yes, it is a function. What qualifies a set of two tuples as a function? Everything in the domain has to map to one thing in the codomain, right? Okay, so very good. So now we look at all the natural numbers and say, well, does every natural number have a factorial of itself? Yeah, okay, that makes sense. Okay, so it is a function. So now we want to look at it and ask, okay, what about f inverse? Does it exist? Can we reverse it? Well, the answer is definitely no. Because if you look at how n maps to z plus in this case, it's a very sparse map. In other words, okay, just give you an example. Look at 3 factorial and look at 4 factorial. 3 factorial is 6. 4 factorial is 24. What about 7? 7, whose factorial is 7? No one's, right? So that means many integers that are non-zero and non-negative do not correspond to the factorial of some natural number. So that means the other way cannot work. It is not a function. The other way mapping back is not a function. So if it is not a function, now how did this get back to the original question I was trying to answer?
About how you can't reverse the logic.
Right, but there was another question that prompted me to talk about whether factorial is inversible.
Why it's not on a calculator?
Oh, right, okay, because somebody asked why there's no inverse factorial on a calculator, and that's the answer, because it is not a bijective function. Okay, well, but this is good because we're relating a topic back to concepts that we have already talked about in this class, even though it was like in the first few weeks of this semester. So that's good. If you relate all of those concepts, that's good. Okay. If you kind of vaguely remember what a function is, something about every blah 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 maps to at least one blah blah, that's still pretty good. Okay. The naming, like what is the domain, what is the codomain, is, I mean, those are just words. But if you remember the every, at least one, exactly one, those are the key concepts. All right. Very good then. Okay, so today is Monday. Let's check out where's our final exam. I think like we have, huh? Exactly 2 weeks from now? Okay. So we can have our practice final on next Monday. You can look up at least 2 existing final exams on Canvas already. I put it here. So this is from 17 fall and this is from 18 Spring. There are additional ones that may be in the share folder. I'm not 100% sure whether I put those there or not. So we can look into the share folder. And in the share folder, everything that has a -FX are final exams. So we do have final exams from 18 fall. So that's only last semester. Huh? There's a whole folder. Yeah.
Final exams up at the top. Yeah, like up at the top.
At the top. Oh. Yeah, but I haven't been keeping it up to date, so it has some really old ones like 16 fall, but I would go backward in time, like start with the most recent ones. If you do have time, then go back a little bit. Just because I do change the way I ask questions, and the most recent one reflects how I have recently thought of asking questions of the same topic, so that might be helpful. So are we doing okay so far? So next Monday is our review session, which means on Wednesday, we can kind of just push our discussion of existing topics a little bit, but I'm not going to introduce any additional topics at this point. So I might go back and talk about Prolog just a little bit, because I think I may not have fully explained the substitution and resolution process, so I can talk about that a little bit. If anyone has any questions about the search algorithms, A-star and Dijkstra's algorithm, we can talk about that a little bit. Yeah, so that's going to be, so we are kind of wrapping up the semester at this point. Any questions before we go? Yep.
When we install Prolog,
Mm-hmm.
do we need to do the system cat requirement on Windows?
I think the Windows version comes with a GUI and an icon. You can just double click on the icon and it fires up the GUI version of SWI Prolog. So I don't think you have to go drop down to command line like I do. But I could be wrong, because I have not really used the Windows version of SWI Prolog. But I believe that it has its own GUI. All right. So I'll see you guys on Wednesday.